So these number of the large elements end up on the left. So if you had a separation of large elements and small elements, K was the separation. You had K of those large guys. They were sprinkled out. After you do this leverage splitter, then at most this many of those large guys would be over on the left-hand side, where they do not belong. And in some sense, the key here is that, the reason why I call this a leverage splitter, is that as you start with something that the number of large elements is already some 1 minus epsilon factor away from n, the halfway point, you get this leverage of happening with the mu, that you get this exponential reduction in the number of guys that will end up on the left-hand side who don't belong there. And this was a factor that was not present in this previous definition. So I think if I tried to sort of pinpoint the one idea that seems to have made the difference between a simple oblivious and a very complicated oblivious algorithm, I think it's that parameter mu. I had identified one thing. All right, so then now this is just now for the sake of the proof. We've got to think about that very simple algorithm actually has, unfortunately, a very complicated proof to show that it becomes a polylog n near sorting algorithm for any arbitrary sequence. So how does that proof go together with this definition? And one of the tools that we use is a classic tool for sorting algorithms, for oblivious sorting algorithms, and something that's known as the 0-1 principle. And this actually dates back to one of Knuth's books. So if you have a deterministic oblivious algorithm, something that doesn't make any random choices at all during the algorithm, we can prove that a data oblivious sorting algorithm correctly sorts all sequences of arbitrary inputs if and only if it correctly sorts all sequences of 0-1s, just bits. So if you just have a sequence of 0s and 1s, if you can show that your algorithm correctly sorts all sequences of 0s and 1s, and it's oblivious, now, again, if you're just using, again, these compare exchanges, it'll sort any sequence. Correct. And there's actually now a randomized version of that, due to Roger Sekaran and Sen in 2005, that if a randomized data oblivious algorithm sorts any 0-1 array with probability at least 1 minus epsilon, then it sorts any array with probability at least 1 minus that epsilon times an n plus 1 factor. So in particular, if we can get a sorting algorithm that just sorts 0s and 1s with very high probability, that's 1 over a polynomial, even still just multiplied by n, still gives you very high probability. You still have 1 over a polynomial, just scratch a 1 off the exponent. So this is going to be the tool that we use for our proof. We're going to focus in on that algorithm that I showed you, but now simplify this input to just be 0s and 1s. So we'll assume that the input is, let's say, k 1s, n minus k, 0s. How well does the algorithm sort that sequence of 0s and 1s? So again, recall that definition of a mu alpha beta leverage splitter, an operation that separates things out the way I had mentioned. What I use is 3 different lemmas, I call the splitter lemmas, to show that there's a constant C such that with very high probability, C applications of that region compare exchange operation will itself be one of 3 things. Either C plus 1, 1/2, 0 leverage splitter, a C plus 1, 2 to the EC with a 4e log n leverage splitter, or a 0, 1/6, 0 leverage splitter. And each of these 3 different lemmas applies to different contexts of the proof. Another concept, now you focus in on using this 0-1 principle, is the concept of dirtiness. So when you talk about using this 0-1 principle, we can assume that our input array now has k 1s and n minus k 0s. So for any region that's supposed to be all 1s or supposed to be all 0s in the end, we can define its dirtiness is to be the number of bits that are of the other type that it currently contains. So if it's supposed to have 100 1s and it has 3 0s, it's of dirtiness 3. and symmetrically. If you have zeros and you have a few ones in it, the dirtiness is the number of ones that are in it. And if a region is sort of where, in terms of the boundary of where that region falls, it is supposed to have some ones and some zeros in it. We refer to that region as a mixed region. And we don't worry about its dirtiness at all. Okay? All right, so in terms of the details, again, I'm just going to skim the surface of the details. It gets kind of complicated after a while. But in terms of a high level of how the proof goes, is what I want to do is to try to characterize the dirtiness of different regions as the algorithm progresses. Again, the algorithm is just doing what it's doing obliviously, but we can try to reason about the effects that it has now by assuming that there's a fixed number k of ones, n minus k zeros, and now ask questions about, okay, what's happening to this array in terms of where are the zeros going, where are the ones going, as this algorithm is doing its thing. And so what you can do is say, okay, there's going to be at some place at that position n minus k where there's a crossover. There's supposed to be all zeros down here, then there's that crossover point, and these guys are supposed to be all ones after that. And then we chop that array up into the little regions of whatever is our current offset size. And now you can index these regions by how far away they are from that crossover point, that mixed region that's there at that crossover moment. So just start numbering things going to the left, numbering things going to the right. Again, we're always splitting by using powers of 2. So, in some sense, we can also have visualized the history of our algorithm too. In the beginning, everything was one giant mixed region, and then we did a split. And let's say maybe the mixed region went that way. This guy, which was this whole left half here, was one region away from the mixed region. You split those guys, and then maybe this became the mixed region. He was one away. This region is one away. This region is 2 away, and so on. So you get these counts. So you can also see that it's sort of like what we teach our kids about heap sort, that in terms of the indices, they kind of more or less double, maybe with a +1 there, in terms of how the hierarchy numbering goes as you go down and down and down. So that's just an indexing issue. And then in terms of the proof of correctness, what I can show is that there's basically 3 different zones, if you will, of sortedness that are going on. There's the mixed region, right at that crossover point from zeros to ones, where it's not very sorted. Things are mixed. You got this mixture of, could be equal number of zeros and ones, and they could be all jumbled in together. No guarantees about that guy. But as you start going farther away from him, the dirtiness is going to decrease at an exponential rate with respect to the distance from that mixed region. And it decreases, decreases, decreases at this exponential rate going down until finally we get some sort of a floor situation where things got so clean that we can't distinguish between just a handful of maybe ones that got stuck in here, and they're just stuck maybe until the end when we do that post-processing step. But there's only going to be a polylog number of those guys. So these what I call extreme regions, they have, their dirtiness is bounded by a polylog n factor. So in terms of the picture of the proof is applying those 3 different lemmas to these 3 different zones. The guys that are pretty far away, either already extreme regions or about to become extreme regions. The guys that are reasonably far away from the mixed region, and their dirtiness is going down exponentially. And the guys that are either very close to the mixed region, maybe even him, and then he gets split. You got to kind of reason about what's happening right there in the middle. So that's how
so your lemma actually spells out the terms, the situations under which each one applies.
Exactly.
And that's quantified in terms of distance from the mixed region.
That's right. In fact, I think I spelled it out on the very next slide. No, I didn't spell that out here.
Okay. But just for each, for different ranges of distance,
yes,
you get different behaviors.
Yeah, I thought I had a slide for that, but apparently not. So, yeah. So here's one of the 3 lemmas, the one that proves that that region compare exchange operation is a C plus 1 1/2 zero numbered splitter.